Today we'll be continuing our session on VCRS or Vapor Compression Refrigeration System. Right. So just to recap, what is a Vapor Compression Refrigeration System? Basically, a VCRS or Vapor Compression Refrigeration System is a system which uses the Vapor Compression Refrigeration cycle. So how does it work? So let's assume that we have two areas. One is our environment. One is the refrigerated space. This is at T1 and this is at T2. So basically we have a refrigerator which consumes work, absorbs heat from the refrigerated space and delivers it to the environment. Okay. So looking at our setup, the VCRS consists of four major components. One is the evaporator. Second one is the compressor. Third is the condenser. Fourth is the expansion valve. Okay, so the evaporator basically is a heat exchanger which is located within the refrigerated space. Now, through the evaporator flows liquid refrigerant which absorbs heat Q1 from the refrigerated space and due to latent heat of vaporization is converted into vapor. Now this vapor is passed into the compressor where it is compressed Now this compressed vapor is at a higher temperature and higher pressure. This passes through a condenser where it rejects heat into the environment and then passes through a device called a expansion valve. Okay, so here we have at the entry of the evaporator, we have low temperature, low pressure liquid refrigerant. Here we have low temperature, low pressure vapor. Here we have high temperature, high pressure vapor. Here we have high temperature, high pressure liquid refrigerant. If we represent this on a TS plot, this is a bell curve for any refrigerant. So we have first evaporation 1 to 2. Let's go this 1, 2. Then we have compression, which is isentropic, so it goes vertically on top to 3. That's 3 0. Then we have constant pressure, heat rejection. 4. And then adiabatic expansion. And back to 1. Now in a refrigeration cycle, we also make do of, or we primarily make do of some plot called pH plot, or the pressure enthalpy plot. So now we are going to represent this same process on a pH diagram. You will find that most of the diagrams are located in a refrigerant and psychometric property table or chart. So you'll find all of these values here for different types of refrigerants. and you will find a plot which looks something like this. So to represent it on pH plot, we have the bell curve, the same bell curve represent here. This is the shape of the bell curve on a pH plot. Now the first process is here, which is a isobaric heat addition. Isobaric heat addition. So this is at a lower pressure, so we have got heat addition here. 1, 2, 2. Next, what we have is compression. This is an isentropic compression. So isentropic compression on a pH plot looks something like this. This is an isentropic line which you'll be able to note, which you'll be able to see on any one of these plots. You'll be able to see these lines which exist for constant entropy. So you can see constant entropy lines. So we follow one of these constant entropy lines to the higher pressure at 3. Next we have constant pressure heat rejection. So constant pressure heat rejection 4, and then isenthalpic or adiabatic irreversible adiabatic expansion. So this comes vertically down back to 1. So this is a representation of a VCRS, vapor compression refrigeration cycle, on the TS plot and pH plots. Okay, so again we have first is constant pressure heat addition. Second is constant entropy compression. Third is constant pressure heat rejection. Fourth is constant enthalpy expansion, which is irreversible. Okay, we're going to be comparing this system to the next kind of system which we also use in refrigeration, which is something called vapor absorption refrigeration cycle. So I'll move this aside. So what we have is vapor absorption refrigeration system. Okay, for a vapor absorption system, refrigeration system works on a similar principle as that of a vapor compression refrigeration system, with one major exception. So let's look at the similarities first. First of all, we have got liquid refrigerant which flows into the refrigerated space. Okay, and this is preceded by the expansion valve, similar to the vapor compression refrigeration system. So we have an expansion valve, we have a evaporator. Okay, before the expansion valve we also have a condenser. Okay, so you can see the similarities here. We have an expansion valve, we have a condenser, sorry, we have a evaporator, expansion valve, and a condenser. The major difference is here, which is this device, which is here. Now, VARS, as it suggests, deals with something called absorption. Vapour Absorption Refrigeration System. Working fluid in a vapor absorption refrigeration system is ammonia. Now, ammonia is the primary refrigerant, or is the refrigerant which is used in this loop. Once this ammonia exits the evaporator, it is introduced into the secondary loop here. Now here what happens is that you have got ammonia vapor which is coming in from here. It enters a tank. This tank contains water. Now, one really interesting principle of ammonia, very interesting principle of ammonia is that it gets absorbed into water very easily. So ammonia gets absorbed with water to form NH4OH, which we all know is ammonium hydroxide. Now this is a spontaneous process. It does not require any energy, and vast amounts of ammonia get absorbed into water to form ammonium hydroxide. So that's what happens here. You have got ammonia entering this chamber, and lots of it gets absorbed into the water. Now this water mixed with ammonium hydroxide is pumped into a device called a generator. So this is called an absorber, and this is called a generator. Now here, this liquid is heated. There is a heat input which is added into this. Now, due to the heating, the reverse process occurs. That is, NH4OH gets decomposed into ammonia and water. So here you have got ammonia exiting. Now this is heated, as this was heated earlier. This is hot vapor ammonia, and liquid water flows back into the absorber. All right. Now, in the absorber, as more and more ammonia is coming in, it's getting absorbed back into the water here. It's getting absorbed back into the water, which reduces the pressure here, which causes more ammonia to flow into this absorber. So this is the loop. Now this ammonia which exits goes into the condenser here where it rejects heat into the environment. It goes into the evaporator where it expands and returns to the rejects heat from the condenser, passes through the expansion valve and gets back into the evaporator. Alright, so this is known as the vapor absorption refrigeration system. So just to recap, a vapor absorption refrigeration system consists of two loops. One, you have got your refrigerant loop, and then you have got your absorber loop. Water loop in this case. Okay, so you've got your refrigerant loop and you've got your water loop. Okay, here we have got liquid ammonia, liquid low temperature, low pressure ammonia, which passes through the evaporator, absorbs the heat from the refrigerated space, is converted to low temperature, low pressure gas or vapor. This vapor enters the absorber, where it is absorbed into the water. Now, as this is being absorbed, the pressure reduces in the absorber, which causes more of the ammonia through flow into the absorber. Now, this concentrated solution of ammonium hydroxide is pumped into a generator. Now, in a generator, you have got a heat exchanger which heats up this concentrated solution. Here you have got ammonium vapor which is generated because ammonium hydroxide decomposes. The ammonia vapor exits and enters the condenser. Here it rejects heat into the environment and is converted into a high temperature, high pressure liquid condition. Then it passes through an expansion valve where it is converted into a low temperature, low pressure liquid state. On the other hand, the remaining water goes back into the absorber.